Okay, so here's our little program. We actually have two versions of it. Can you explain what this program does here?
So you check, so go from I is 1, you check up to 10, or whatever n is, and you go up by 1 every time.
Okay.
Oh, and now you have, for every I, you check for j is 1, and it goes up by 1 until it's less than or equal to the square root of I over 2.
And why did we, it was hard to figure out that we had to stop checking there. Like, why do we stop checking at the square root of I over 2?
Well, I guess you could, like, there wouldn't be any new cases over that because you would just get, like, double cases. Like
Yeah.
for 5, you could get 1 and 2 and 2 and 1. And you want to not get that.
Right, and why was square root of I over 2 the good place to stop?
Because it helped us not count these doubles that counted like
Yeah.
1 squared plus 2 squared and 2 squared plus 1
Right,
squared.
but why square root of I over 2? Why not square root of I over 10 or just square root of I?
Because square root of I was, well, we thought it was that originally, but that gave us a few overcounts with some smaller numbers, but square root of I over 2 was, I guess, just what we found the smallest, or the smallest number of numbers we needed to check that eliminated all the doubles.
Yeah, it worked, but my question is, why did that work? What was the problem we were solving? We're looking at here.
Double counting, like counting some of the squares that's the same as.
Okay, so we're looking at sums of squares.
Yes.
Yeah.
So we made j squared got to I over 2. Or, yeah. So that means our other number, which I guess we said was a, could also get up to I over 2, but they couldn't overlap.
Okay.
So we didn't have any we didn't have any overcounting.
So at square root of I over 2, that's halfway.
Mm-hmm.
And we tried a bunch of different things first, and then we came to understand this, and it's sort of obvious after the fact. But finding it was not super obvious. All right, and what does this program do then, the first one?
So a is the square root of I minus j squared. So if you start with the number I and you subtract a square from it, and if that number is a square, then you have a sum of squares that works.
Okay.
And if it's an integer, you print it and you say the sum of squares.
All right, so let's run it. All right, so there they are up to 10. 2 is 1 squared plus 1 squared. 5 is 1 squared plus 2 squared. 8 is 2 squared plus 2 squared. 10 is 1 squared plus 3 squared.
Yep.
Right? But we could make this go up as high as we wanted. How high do you want to go?
Let's go up to 100 maybe.
100, okay. And we'll just scroll it to some random place. Do we see any duplicates?
Oh, 85
Well,
has
85 has 2.
but they're different.
Okay, so that means 85 is not
65.
prime.
You saw 65 had 2.
65 has 2. Is that on screen? Yeah, it is. Oh, 65 is actually the one we played
Yeah,
with.
Yeah, 1 and 8, 4 and 7.
How lucky. Okay. All right, so that's neat. So then we did a second program which operates a little bit differently. What does this one do?
So it's basically the same program, except what we display is how many possible combinations each number has.
Okay.
So if we were to run it, it displays every number from, in this case it's going to be 1 to 10. And it shows which ones have them and which ones don't.
Yeah.
And how
Okay.
many. Like
2
Alright.
had 1, 5 had 1, 8, and then 10.
All right, so let's see if we can find the first one. We know there's the ones that have doubles up to 100, so let's see if we can find the first one that has a double.
Yeah.
2,
2,
50.
50. 50 is 2.
All right, what are they? That one we can probably figure out in our
So
head.
1 and 7 works.
5 and 5.
1 and 7 and 5 and 5. So 50 is the first one and has 2.
65
Next up, the next
again.
one's 65.
That we saw, and
65.
85 we saw.
Yeah, 85 is the last one. Or but there's another one.
Alright. Is there another one?
Oh, I just getting confused with it now. I think it's just the scrolling.
Yeah, so what we can do actually here, oops, sorry, I scrolled all the way to the top. Instead of just printing out the count, how about let's do that only if the count is 2 or greater.
Alright.
If count is bigger than 2, bigger than or equal to 2, how about just bigger than 1?
Alright.
We'll print it, and that should. Did I mess something up?
If equals.
Oh, I sure did. All right.
65 and 80, so those were the only ones.
So we can go to 1,000 now.
2.
And we can probably see the first.
Let's see, we're only getting. Oh no, we get.
Did we get a 3?
I see a 3. Yeah, 325.
All right.
25.
So sorry for scrolling so much. If I can actually check we can find the 3s very easily.
325. So let's see, there's only multiples of 5, but I saw some in the 2 list that were not multiples of 5.
Huh. All right. So now maybe we'll go to 10,000 and we'll check. Let's see if we can find the first one that has
4.
4.
No, we actually
A
get
fair amount of them.
still only multiples of 5.
Yeah, that's interesting.
Interesting.
I guess multiples of 5 we just have a lot of factors. I wonder if we have any 5s.
Takes a bit to run.
Did I?
No, we
Yeah.
had one that's 6, 5525.
Oh wow! There's one that has 6 before we get 6 before we get a 5. That's kind of neat.
Yeah.
2 6s and 2 5s. 10,000.
Yeah. So I don't know why it's all 5s there, all multiples of 5. You said you saw some in the 2 list that weren't multiples of 5.
Yeah.
Do you remember what they were?
I think 221, I think. Might have worked. Yeah. 221.
Is that on screen?
It's like the only
one.
Huh. Okay. Well, it looks like there's interesting things even going on beyond the simple stuff we looked at. So maybe there's other things we could explore here. Why is it that these multiples of 5 are so
Good at.
so good at being represented in multiple ways? All right. Good job, guys.